All right, we talked about energy before. We talked about power. Power is the rate of usage of energy or energy over time, right? We've seen that before. And so therefore, you could say that energy is equal to power times time. And with electrical circuits, we've seen things, you guys are familiar with maybe a 60-watt bulb or a light bulb, right? Well, the idea of a watt is energy over time, right? Remember, power is measured in watts, and a watt is equal to a joule per second. So a 60-watt light bulb uses 60 joules per second. Those are the same thing. We need to mute their mic there. All right, so it's going to use 60 joules of energy every second. Somebody please mute their mic. Now, let's look at tying this together, though, because we got another equation for energy. Doesn't energy also relate to voltage? Energy is charge times voltage, QV. Well, then we can relate power to voltage as well. If power is equal to energy over time, then I can substitute QV right in for energy, and I get a new equation for power. QV over T. And you might even notice, look what I have here. What's Q over T? Well, that right there is current. I, charge passing through over a period of time, which means we now have an equation for power, P equal to I times V. A nice simple equation. You have Ohm's law, V equals IR, and now we have power, which is in watts. Current is in amps. Voltage is in volts. Right? Notice a watt is a joule per second. An amp is a charge passing through every second. A volt is a joule per coulomb. And notice how the units cancel out. And I get joules per second is equal to joules per second. All right, so for any circuit element, if I know the voltage drop and I know the current, I can figure out the power consumption of that unit, of that circuit element. And if I combine that idea with Ohm's law, since V equals IR, you actually have a couple variations of the same circuit using some substitution. Well, then power would equal I times IR, right? P equals IV if V equals IR. And so I have another equation, P equal to I squared times R, just by combining Ohm's law and P equals IV. And since I is equal to V over R, we can also say that P is equal to V over R times V, which gives you P equal to V squared over R. So you have three forms of the same equation for power now. And you have P equals IV, and then if you combine it with Ohm's law, you get I squared R or V squared over R. And the last thing I want to look at is this idea of an energy unit of a joule. Because your electrical bill doesn't give you energy in joules. All right? An energy unit is in joules, but there's also other forms that we can write it. Well, since energy is equal to power times time, then it's equal to a watt times a second. All right? 1 watt second is equal to 1 joule. Those are the same thing, a watt second. Well, On your electrical bill, you're going to get a unit called a kilowatt hour. A kilowatt hour, not kilowatt per hour, but a kilowatt times an hour is equal to 1,000 watts times 3,600 seconds, right? An hour, 3,600 seconds, right? So this is what a kilowatt is, and this is an hour. And so you have this unit for energy called a kilowatt hour that's equal to 1,000 times 3,600, or 3,600,000 joules of energy. All right, so your phone bill, or your electrical bill rather, will measure the amount of kilowatt hours you use, and then they bill you for kilowatt hours. 1 kilowatt hour on your electrical bill might be in the range of 15 cents. And so now you can quantify how many joules you use in a unit called a kilowatt hour, and you can bill per kilowatt hour. It's only 15 cents per kilowatt hour. So we're going to use this and start to calculate the cost of using our electricity in our home. But I want to introduce that P equals IV equation because I'll throw some questions on the web assignment for the next one here.